Okay, so in this video we're going to talk about Feynman diagrams. Okay, you are responsible for being able to interpret Feynman diagrams as well as draw simple Feynman diagrams on your own. Okay, now the good news is that for the most part, there's not a ton of different Feynman diagrams that you would be expected to solve at this level of physics, and so as long as you do a good job in preparing and you know, read the textbook and the examples in the textbook and the examples at the end of the textbook, you should be pretty well prepared, hopefully. Okay, so a Feynman diagram, the idea of the Feynman diagram was basically created by the physicist Richard Feynman, who's one of my favorite physicists of all time. And basically what it is it's a way to graphically represent very complex, or I guess it could be simple, but complex particle interactions in a way that's easy to visualize. Okay, so again, for the purpose of this course, you need to be able to understand and draw basic Feynman diagrams. A Feynman diagram is typically drawn in one of two ways. It's typically drawn either with the space axis on the y-axis and the time axis on the x-axis, or sometimes they have these flipped. And I realize it's very annoying to not have a consistent way of doing that. It also annoys a lot of IB physics teachers, but most of the time you can tell from context how you're supposed to draw these. Okay, now I will also say in a lot of the problems we're going to be doing, we're going to have time on the x-axis and space on the y-axis, but be prepared to creatively interpret some of the Feynman diagrams based off of the fact that sometimes the axes could switch, and sometimes they're not even labeled, and so you just have to tell from context which one is which. Okay, so I apologize for that, but hopefully you'll understand more as we go through Feynman diagrams. Okay, so these are just a whole bunch of different Feynman diagrams, and at first it looks like a bunch of arrows and squiggly lines, which it is basically. But as we go through, hopefully you get a better understanding for what different things represent. Okay, so again, the physicist Richard Feynman developed this graphical way of representing particle interactions that could be used to predict the probabilities of the outcomes of particle collisions. Okay, and again, you typically have two axes, a space axis and a time axis. Okay, so just to kind of, lead us off here, suppose you had two electrons approaching each other, okay, one from the top of the page and one from the bottom of the page. Now, of course, we know what happens if you bring two electrons together is they are going to repel because of the Coulomb force. Okay, the Coulomb force is part of the electromagnetic force, okay, which means that, as we talked about in the last video, the way they repel is by the exchange of photons, okay, because the photon is the exchange particle for the electromagnetic force. Okay, but let's say we've got these two electrons, they repel, okay, like so. And if we draw these particles as arrows, which you always draw particles as arrows in a Feynman diagram, there's a space between the arrows where something happens. Okay, what they call the bubble of ignorance on this slide. Okay, now of course we know what's happening in that bubble of ignorance. And then afterwards, of course, the electrons repel. We know that somewhere in that bubble of ignorance is the exchange of those photons, which is the exchange particle for the electromagnetic force. But the bubble of ignorance is the actual place in the plot that exchange particles do their thing, so to speak. Now, if you were to add a time axis, this sketch would look something like this. Okay, two particles come together, they exchange something. Okay, and then afterwards they go apart in space. Okay, and so this is an example of a Feynman, or part of a Feynman diagram. Okay, so again, the arrows represent the particles. If the time axis is on the x-axis, the way you read these is always from the start of time to the end of time. So if you have the time axis on the x-axis, then you would start reading on the left side, okay, right over here, and then you would read left to right. Okay, so right here we have two arrows, which means we have two particles. The particles are approaching each other in space. Something happens here, and then after that something happens, the two particles go away from each other in space. Okay, now of course, again, we know what's happening is that the exchange particles are being passed back and forth between the electrons. That exchange particle is the photon, and then after they exchange that photon back and forth, then they repel. Okay, and so the Feynman diagram will help us see that. Alright, so just to give some general guidelines for Feynman diagrams, and I guess, yeah. Okay, so some guidelines. Number one, I said this before, but particles are represented by straight arrows, just like the two electrons in the last example that we did. Exchange particles, aka force carriers, are represented either with wavy lines or curly lines. Okay, the curly lines are only used if the exchange involves the strong interaction. Okay, so the green wavy lines represent gluons, which is the exchange particle for the strong nuclear force. Okay, the squiggly line you would use in situations where you have either the electromagnetic force or the weak interaction. Okay, so those squiggly lines could either represent photons, which are the exchange particles for the electromagnetic interaction, or the W+, W-, or Z particles, okay, which are exchange particles for the weak interaction. Notice, by the way, that the electromagnetic force and the weak interaction have the same symbol. The reason is that we have actually discovered in recent years that if you look closely enough, the the electromagnetic force and the weak force are actually different parts of the same force, which is why those two forces have the same symbol for their exchange particles. Okay, even though the exchange particles are completely different, we still use the same symbol for that. Okay, so some more guidelines for drawing Feynman diagrams. I said this before, but straight arrows represent particles, wavy lines represent exchange particles. The vertex, that is where two arrows meet, represents an interaction between two particles. You must have one arrow going in and one arrow going out of a vertex. And most importantly, particles drawn going backwards in time are antiparticles. And that's the one that always messes with people the most. They say, how can you have a particle going backwards in time? I wouldn't think too much about it right now, because it'll just hurt your brain. Let's just say, for the sake of drawing Feynman diagrams correctly, you draw antiparticles going backwards in time. And when I say backwards in time, I'm talking about each particle is an arrow, right? And so whichever way the arrow is pointing represents either going backwards or forwards in time. Okay, these next few slides just kind of repeat the things I just said. It's definitely pause it if you need to go through any of these more slowly. Okay, notice here it says the x-axis on a Feynman diagram represents time and is read from left to right. That's not always true. As I said before, the IB is horribly inconsistent with this, but it is mostly true. Okay, so again, you always read a Feynman diagram starting at the beginning of time and moving forwards in time. Okay, so in this situation, what we're looking at the Feynman diagram for is, if you imagine time on the x-axis, then you would start reading this on the left side. Okay, so let's say we start over here. We have two particles. One is going pointing forwards in time, that's labeled as an electron. The other is pointing backwards in time. Okay, and if it's pointing backwards in time, it must be an antiparticle. In this case, it is an anti-electron, aka a positron. Okay, as time progresses forward, that means as we read from left to right, we notice that the space between these particles decreases. They meet right here. And then you have to think, what happens when an electron and an anti-electron meet? Well, that causes annihilation. Okay, we talked about that in the very first video. When a particle and antiparticle meet up, they cause annihilation and they produce energy in the form of photons. Okay, and so if you continue reading from left to right, you can see that you end up with no particles, just a squiggly line which represents a photon. This is the symbol for a photon. Okay, so this is the Feynman diagram for annihilation. Okay, so very simple Feynman diagram. Obviously, normally it would not be labeled. It would just have the arrows on the squiggly line, but this is the Feynman diagram for annihilation. Okay, so going on, I want to look at some more examples of Feynman diagrams. Okay, so here we have two Feynman diagrams. The top one is showing the repulsion of two electrons. Notice again that you always start reading a Feynman diagram from left to right, or I shouldn't say that, from the beginning of time to the end of time. So in this case, it would be from left to right. You start off with two arrows, okay, representing electrons. The arrows approach each other in space. At some point, they exchange a photon. Okay, so here and here you can see the photon being exchanged. And then if you keep moving forwards in time, you can see that the electrons just go apart in space. Okay, so this Feynman diagram represents the repulsion of two electrons. Okay, for the bottom one, we can see we start off with one electron. Again, you always start at the beginning of time and move forwards in time. We start off with one electron, just kind of going through in space. It just kind of spontaneously emits a photon right here, and after that happens, the electron goes in the opposite direction in space. Okay, so these are just two basic examples of Feynman diagrams. Okay, so just to see a few more. Okay, here, notice that time is still on the x-axis, and these arrows are all pointing backwards in time, which means I'm dealing with antiparticles. This is basically two positrons repelling each other, so it looks almost the exact same as the diagram, the Feynman diagram for two electrons repelling each other, except all of the arrows are pointing backwards in time. Okay, now just to do a quick example to see if you can correctly interpret Feynman diagrams, here are four different Feynman diagrams. Okay, and let's see if you can match these up. Okay, so let's say this is going to be number 1, this is going to be number 2, this one is number 3, and this one is number 4. And let's say this is A, B, C, and D. Okay, so for this example problem, let's see if you can correctly match which Feynman diagram goes with which description. Okay, so pause it here, see if you can take what we've learned about Feynman diagrams so far and interpret what they're saying, okay, and match which diagram goes with which situation. Okay, so in other words, the situation right below the Feynman diagram might not actually correspond to the correct interpretation. Okay, so in other words, the answer choices on the bottom are all mixed up. Okay, so pause it here and see if you can figure out which of these diagrams go with which situation. Okay, so let's see if you got these correct. Okay, so number 1, we had an electron emitting a photon, and then it keeps going. Okay. Number 2, it was almost the exact same situation with a positron. Number 3, we had a positron and electron causing annihilation. And then number 4, we had pair production. Okay, a photon spontaneously produces an electron and a positron. Okay, so pause there if you need to look at that some more. Notice, by the way, on these Feynman diagrams, the axes are not drawn, and so you kind of have to infer from context that time is on the x-axis. I will say if it's not clear, it's usually safe to assume that time is on the x-axis, but sometimes you can tell from context whether or not that's the case. Okay, just to show you some more examples of Feynman diagrams, here we have pair production, here we have annihilation. I think we've seen both of those before. Okay, so let's get into a more complicated type of Feynman diagram. Okay, so what we have here is we have a Feynman diagram that represents a down quark emitting a W minus particle, and the W minus particle decays into an electron and an anti-neutrino. Okay, and this is a very, very, very important type of reaction that you need to be able to recognize. And so again, what's happening here, if you read from the beginning of time to the end of time, you start with a down quark. Over here, that's what the D represents. The down quark emits a W minus particle right there. That's the squiggly line. Okay. In exchange, haha, no pun intended, the down quark becomes an up quark. Later on, this W minus particle is going to decay and produce an electron and an electron neutrino. Okay, now it's also important for me to point out that charge has to be conserved at each of these vertices. Okay, so notice because it's a W minus particle that has a charge of -1, when that W minus decays, the overall remaining charge still has to be -1. Okay, and so the electron carries that charge. Also notice that the down quark has a charge of -1/3. Let me reset. Okay, so a down quark has a charge of -1/3. And when it loses this charge of -1, okay, right here it's losing the -1 charge from the W minus, what's left over has a charge of 2/3, which is the charge of an up quark. Okay, so you can apply conservation laws at each of these vertices. Okay, and that's important because sometimes you're asked to make predictions about what some of these other particles might be based off of those conservation laws. Okay, now the reason that this particular Feynman diagram is so important is because this is actually the Feynman diagram that represents beta minus decay. Okay, so this is beta minus decay. In beta minus decay, a down quark within a neutron decays into an up quark, okay, which changes the particle from a neutron to a proton, and then in the process, okay, this process that we're looking at right here also ends up emitting an electron and an electron neutrino. Okay, so this is a very, very commonly seen one that you definitely need to be able to recognize. This is for beta minus decay. And on the next slide, we'll see basically the exact same reaction written slightly differently. Okay, we have a neutron, okay, decaying into a proton. The way it does that again is by emitting that W minus particle. The W minus particle is going to decay into an electron and an anti-electron neutrino. Okay, notice, by the way, I believe, if I'm not mistaken, oh, okay. On the last slide, I didn't point this out, but this should actually be an anti-electron neutrino. Notice how this arrow is pointing backwards in time. Okay, so in beta minus decay, you get an electron plus an anti-electron neutrino in order to conserve lepton number. Okay, and what's happening if you were to break down the neutron and the proton in terms of their quarks, what's happening is that within the neutron, one of the up quarks stays the same, one of the down quarks stays the same, but one of the down quarks decays into an up quark, which changes a proton into a neutron, plus you also end up getting this W minus particle that comes out and then decays into the electron and the electron antineutrino. Okay, so that's basically how beta minus decay works at the most fundamental level. Okay, so pause there, make sure you fully understand that. Okay, you would also be expected to recognize the same thing for beta plus decay. Okay, let's take a look at one more example. By the way, notice this is a situation of one quark changing into another type of quark, which means that this involves a weak interaction. Okay, remember, the only time one quark changes into another type of quark is through the weak interaction. Okay, in this next example, we're asked to explain what's happening in this Feynman diagram based off of just looking at it. Notice that we don't have any changes in the type of quark, but this is the symbol for a gluon, which is the exchange particle for the strong interaction. Okay, so we have an up quark emitting a gluon, and then the gluon is going to decay into a down quark and an anti-down quark. Okay, which again is not going to be very stable because the down and anti-down are quickly going to annihilate each other. But that's still how you would answer the question. Okay, and just to show you a few more examples. Okay, beta plus decay, which we've all seen before. The Feynman diagram for that would look something like this, very similar to what it was before. Okay, but in this situation we have a proton decaying into a neutron. As it does so, notice that it emits a W plus particle. A common question I get asked is, how would you know what type of particle this is if they didn't give it to you? Because that is a question they ask sometimes on the IB exam. Sometimes they won't tell you what this exchange particle is, and they'll ask you to figure it out. And the way you would do that is from conservation of charge. Because right here, at this vertex, charge has to be conserved. Okay, the proton has a charge of +1. The neutron has a charge of 0. So the proton comes in, two particles come out, the neutron and this mystery exchange particle. If the neutron has a charge of 0, then the mystery exchange particle must have a charge of +1. And the only exchange particle that has a charge of +1 is W+. Okay, also notice that W+ is going to decay into an anti-electron. Notice the anti-electron is going backwards in time, and the electron neutrino, which is going forwards in time. Okay, so that is the Feynman diagram for beta plus decay, and both of these you need to be able to recognize. Okay, the picture on the left and the picture on the right are basically the same. They're just represented in slightly different ways. This on the right is showing you kind of more on a individual quark level what's happening. Okay, but they both represent the exact same thing. Okay, so that's W plus again. Okay, and just to show you one more example, it says the Feynman diagram below represents a beta minus decay via the weak interaction. This is actually from a past IB exam. And it says the exchange particle in this weak interaction is a virtual particle. State what is meant by a virtual particle. Okay, we'll come back to that question in just a second. But the second question says determine whether the virtual particle in the process represented by the Feynman diagram is a W+, W-, or a Z0. Okay, now again, the easiest way to figure that out is based off of conservation of charge. And we can do that either here or here. Okay, I'm going to look at the second one, because if this is beta minus and this is an electron that has a charge of -1, any neutrino has a charge of 0, and so that means whatever this virtual particle is right here, if it's decaying into an electron and an antineutrino, it also itself must have a charge of -1. And so this would definitely be a W- boson, and then you would explain why because of conservation of charge, blah, 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 blah. Okay, so that's just to give you some idea of the types of questions you might see about that. Okay, now your worksheet has many more IB questions. I would definitely make sure that you're able to do all those questions, that you're able to do all the sample calculations that are in the textbook within the chapter, and all the questions at the back of the chapter. Okay, because again, there's only so many different types of problems involving Feynman diagrams that you can expect to see. Okay, so I realize drawing and interpreting Feynman diagrams is one of the more complicated parts of this unit. Okay, so please rewatch this video as you need to. As always, please let me know if you have any questions, and I will see you guys in the next video.